This video shows you how to start up the Leica SP8 STED microscope and add a sample to an air or oil immersion objective. To the right of the microscope, next to the room door, switch on the wall plug for the Leica compressor. Behind the laser rack and monitor, ensure the 4 wall plugs are switched on. The PC will already be on, but the monitor is off. On the right of the PC desk, switch on the 3 green switches for microscope, scanner power and laser power. Lean over the PC desk and to the right switch on the HXP fluorescence lamp. The microscope will continue booting, as can be seen from the microscope touchscreen. Whilst waiting, switch on the laser safety key switch adjacent to the green power switches. On the laser rack to the left of the monitor, ensure the top box, the white light laser, has a key switch turned to on. If you are intending to perform STED, you will also need to switch on the required depletion lasers underneath the white light laser. Depending on your dyes, choose a 660, 592 and/or the 775nm lasers. Each laser has its own power switch and key switch. If needed, power on the 660 or 592 and then turn the key switches. If you're using the 775nm laser, turn the key switch to on. To add your sample to the stage with an air objective, tilt the condenser arm back to allow easy access to the stage. Using the touchscreen, press the Z Control tab and then hold the Move to Load button to bring the objective down. Bring your sample in through the upper access hatches and carefully add your slide to the stage, ensuring it is cover slip downwards towards the objective and flat. Ensure the sample is held in place with the 2 spring clips. Using the Smart Move controller, move the stage in X and Y to position your sample above the objective. Then finally, bring the condenser arm forward again. In the Z Control tab of the touchscreen, hold the Move to Focus button to bring the objective up to approximately the focal plane, as shown by the Z plane reading 0 micrometers. Click the Contrast tab and choose your preferred illumination method. Here we choose Fluo for epifluorescence. Then choose the filter cube to suit your sample and open the lamp shutter with the IL shutter button. Now you can use the Oculus and Smart Move controller to fine-tune your position and focus. To use an oil immersion objective, firstly check the objective chosen on the touchscreen overview tab. Here it states it's a dry objective. Click the Objective tab and choose an oil immersion lens. Note there are 2 63 objectives. The first is a water immersion lens. The chosen objective will flash, signifying that you need to change immersion type. Now add oil onto your cover slip. Using the applicator attached to the lid of the oil bottle, collect a small drop of oil on the end and carefully apply a drop to your cover slip. Place your sample in the stage holder, cover slip downwards towards the objective and flat. Ensure the sample is held in place with the 2 spring clips. Using the Smart Move controller, move the stage in X and Y to position your sample above the objective. Bring the condenser arm forward. On the touchscreen, once more press the chosen oil immersion objective button. It will stop flashing and move the turret to that objective. If you are starting without having found your sample on an air objective, use the Move to Focus button in the Z Control tab to bring the objective to approximately the correct focal plane. Be aware that there are 2 similar icons at the bottom of the touchscreen. Do not press these as it resets the saved planes. Finally, using the Contrast tab, choose Incident or Transmitted Light and your preferred technique. Here we choose fluorescence and, as before, choose a filter cube suitable for your sample. Open the shutter with the IL shutter button. Now you can use the oculars and smart move controller to fine-tune your position and focus, remembering to close the lamp shutter when finished to prevent damaging your sample.
The Leica SP8 uses LSX software. The first window you will see when you switch on the system is under the Acquire tab, and it is used to set the main parameters. However, you need to switch on the lasers, or at least check that are already switched on. To do that, you need to move from the Acquire window to the Configuration window. Click the Configuration tab, make sure that you have laser config on, and switch on both lasers. The white light laser is set as in standby 12% and 70% when you use it, so that is fine. Click Acquire and you go back. Once you are back in the Acquire window, you should start setting the format of your image acquisition, the speed of the scanning laser, and the direction of the scanning laser. At the beginning, the format is 512 by 512. Please go 1000 by 1000, set speed to 600 and set bidirectional on. I will explain later on what all of this means. The Leica SP8 can acquire in several different ways. The most basic one is just a single plane X and Y acquisition. However, you generally need at least a 3D image acquiring on the X, Y, and Z plane. This is achieved acquiring a sequence of X and Y images and changing the focal plane. You can do that on the acquisition mode, where you can select X, Y, and Z. As you can see, there are several different acquisition modalities that you can use if you wish, including lambda scans that allow you to acquire the same image at different wavelengths. Additional acquisition modalities includes tile scan and mark and find. Tile scan allows you to acquire a large image using smaller images than they are stitched together, while mark and find allows you to preset X and Y position for several acquisitions and do it automatically. This can be done in a manual way or using a very useful navigation tool. Next step in setting up this imaging acquisition is to tell the system which lasers you are going to use to excite your fluorophore and which detectors you are going to use to capture the photons coming from it. The Leica SP8 has a fixed line 405 laser to stimulate on the UV range and a white light laser. The white light laser actually is 8 lasers in one that can be used at the same time, allowing you to stimulate with nanometer precision between 470 and 670 nanometers. So you can choose and tune the stimulation exactly to optimize the output from your die. The system is very flexible. Not only the white light laser allows you to stimulate pretty much wherever you want, but fully tunable detectors allow to capture photons on the window that you choose. This allows you to get the best out of your fluorophores. The system has 5 detectors, 4 for fluorescence and 1 for transmitted light. The number 1 and number 3 are very sensitive hybrid detectors, while number 2 and number 4 are standard photomultipliers. I suggest you to use the hybrid at any time, since they are much more sensitive, meaning that you will need less light to stimulate your fluorophore, reducing the chance of bleaching them. However, if your sample is really bright, you might blind the hybrid detectors. In this case, you can use standard photomultipliers. The system allows you to acquire one or more fluorophores at the same time, or you can acquire them one after the other. Acquiring fluorophores at the same time, let's say in the same sequence, is faster. However, is a little bit dangerous, since you might get what is called bleed through, so unwanted, unspecific signal from one fluorophore to the other. The SP8 is really fast, so my suggestion is to acquire in series, so one channel after the other. Yes, it is a little bit slower, but being the system very fast, you will get a quick imaging and at the same time you avoid risk of bleed through. In this image, you see that hybrid 1 and photomultiplier 2 are on at the same time, as well as the 405 laser and the white light laser. One of 8 output of the white light laser is on at 499. What you need to do now is to choose which laser or which lasers you want to be on and which detectors you want to be on. If you click the sequence button, you can start creating sequences that allows you to add lasers and detectors at different sequences that will be acquired in series, meaning one after the other. What I have just done is first of all creating sequence 1 and switching off photomultiplier number 2. So in this sequence only the hybrid 1 is on. So my system started with no sequences. I have created one, and in this one I had 2 detectors and 2 lasers on at the same time. I don't want this for my experiment, or at least for this training, and I'm going to switch off both the white light laser and the photomultipliers for this first sequence. Then I'm going to create a second sequence, clicking the plus button. Switch off the detector, switch off the laser, click plus and create a second sequence. This second sequence is an exact copy of the first one. However, on this second one I want to do something different. I want to have only the second detector on and only the 499 on. So I'm going to switch the first hybrid detector and I'm going to switch the 405 laser. Once that the sequences are set, you need to adjust the 2 main parameters for an acquisition: laser power and the detector gain. Increasing the laser power, you're sending more light to the sample that will be reflected back. So more light in, more light out. This is good. However, you risk to bleach your sample. To get a brighter image, you can also increase the detector gain. So you just amplify the photons that are coming out. Doing so, you will also amplify the background noise. So you get a brighter image, but is more grainy. Balancing the amount of laser that you are using and amount of amplification, you will get the best possible image. If your sample is very strong in terms of not being bleached, you can use more laser. You will get a higher quality image. However, if your sample is very delicate, you need to use a very low amount of laser and increase the gain. Now let's set the first channel to acquire on the UV range on my convallaria sample. As you can see, now I have the 405 laser on, you see the red button, set at 1% laser intensity. I also have the first hybrid detector on that acquires from 410 and 462 nanometers. This icon here shows that the channel will be displayed in grayscale. If you want a different color, you just have to double click and choose the color. Blue, for example, and then you can click live. This allows you to see your sample on the right hand side of the screen. Once you have your sample, the first thing that you might want to do is to zoom in or zoom out so that you image just the area of interest. You do this using the slider in the software, or you can use the knob on the desk. Next step is finding the right focal position. You can do it moving the sample up and down using the focus knob on the joystick or using the one on the panel on top of the desk. Doing so, you will see that your sample will get brighter or dimmer depending where you are. When you will be on the central focal plane, your sample will be at its brightest, and that is the right position for you to start setting laser intensity and gain of the detector. As you can see, I'm moving now the focal plane down, the sample gets dimmer, and now up again and the sample gets brighter. When it is at its brightest, or at least when it is on a position that is good for you, you can stop. Using the virtual joystick, as I'm doing now, you can also finally move your sample in any direction. And finally, you can adjust the slider to set the right display brightness for your sample. Remember that using that slider, you are just changing how the monitor displays the image to adapt it to your human eyes. You're not actually changing the brightness, the number of photons coming out from the sample itself. Now it's time to properly set the laser intensity and the detector gain of the channel or the channels that you are acquiring. The main point is to have enough light so that the sample can be detected, but not to have too much light that will blind the detector. Generally, the Leica SP8 is set to detect from 0 to 255 level of intensity, an 8-bit detection. This can be changed up to 4096, but generally 256, 0 to 255 is enough. So you need to make sure that the light coming out from the sample will be inside this range. How you do that? You can use the display that you have now, that is a blue scale. However, since our eyes are not very sensitive to variation in brightness, you can use a color code images that transform brightness in colors. I show you how to do it. If you click that button, the image will be transformed in a range of green, orange and blue. In this false color image, any pixel that is green means that has an intensity of 0. That is good if it is your background. However, if you have intensity 0 from a part of your sample that actually is your sample, it is an interesting area, it means that you're not using enough light. Anything that is blue means that that specific pixel is oversaturated, so it is beyond the detection level, and this is not good because you are losing information. Anything that is measured as more than 255, displayed in blue on the screen, will lose the real amount of brightness that is inside that pixel. So you need to make sure that everything it is actually in the detection range that in this image is displayed from 0 to 256. So any pixel that is in this range of color is good. So let's see how to do that. You can zoom in to see the image more properly. Now you can see the single pixels. The intensity of those is 255. Anything displayed in green is 0. So now, changing the laser intensity or the gain, in this case I'm changing the laser, I'm going down, so the light is lower and the number of oversaturated pixels is lower. If we zoom in, I create a window to zoom in on my area of interest, you see that all the interesting pixels are within the detection range. As I said before, getting the right parameters is a balance between laser power and gain. Now, changing the gain, in this case going down, I reduce the intensity of the pixels. The image is very dark. Now I can counterbalance this going up with the laser. This balance depends on the kind of sample that you have. Now you can keep increasing the laser until you are within the full detection range. Again, if you change the position of that slider, you change how the image is displayed. However, this will not affect the intensity of the light detected by the system. Now that the first channel is set to acquire on the UV range, I want to add a second channel to acquire on the green range, pretending that I have a green fluorophore on my sample. To do this, I click the sequence button, the sequence panel appears, and I will click plus. What's happening now is that LaSex, the software, creates a second sequence that is exactly the same as the first one. I will use the first one as a template, modifying it and set the right parameter to acquire on the green area. As you can see, they're exactly the same now. So the first thing that I want to do is switch off the detector number 1 and switch on the detector number 3. I check that the laser of interest are on. The one that I don't need will go off in a moment. I show you how to do it, but the first thing I want, now that I have just switched on the 470 laser, and I want to move the detection range for the hybrid detector 3 on the green range. You set it to the position that you want. You can move both the detector and the laser so that the excitation peak can be changed as you wish, just typing in the peak detection. You can move the slider representing the acquisition range. You can do it dragging the side of the window or just typing in the detection range. Once you're happy, you can click Start and see what's happening. You can see that two channels are acquired at the same time. This is not what I want for this acquisition. There's nothing wrong with that. Acquiring two channels at the same time speed things up, but I would like to show you how to acquire one channel after the other. It is a little bit slower, but it is safer. Avoid any risk of bleed through. The reason why now the system is acquiring two channels at the same time is because the transition between sequence 1 and sequence 2 is set as between lines. So the detector are always on and the laser will switch quickly on and off so that the light it is captured by one or the other. We don't want that. We want a transition set as between frames or between stacks. Those two options are exactly the same as long as you acquire a single X and Y image. It will be important to choose between those two once we will acquire in 3D, and I'll tell you about it in the next 10 minutes. So now I stop the acquisition. Otherwise you cannot select what kind of sequential scan you want. You select between frames or between stacks and you click live again. Now you can see that a single channel, the channel in the green range, is acquired. Again, I can change how the colors are displayed on the detector hybrid 3. I decide to have it in green. I can change how it is displayed on the right hand side as a black and white grayscale, the green scale that I chose before, or the false color that allows you to set in the best possible way laser intensity and gain. From now on, things goes pretty much the same as you have done before for the sequence number 1. Now that both channels are set, you are pretty much ready to acquire your image. However, there is one last but very important parameter to set. That is the format. Here we set the acquisition format to 1024 by 1024. This is the number of pixels that make up your image. The real size of your image depends on the magnification of the lens and the zoom that you have applied. To acquire the image properly, without losing any information or without getting a file that is too big, you need to set the right amount of pixels, so the right format. Changing the number of pixels but keeping the size of the image the same means that you are de facto changing the pixel size. You can do it manually, or you can let LassX to do it for you, finding the best trade-off so that you don't get a file that is too big, but you don't lose information while you are acquiring. How you do that? You need to click Optimize Format. You see it goes from 1024 to 136 by 136. This is where we were before. So doing so, you might have noticed that the pixel size changes. The higher the number of pixels, the smaller the pixel size. So if you are trying to put into the same image that has the same size more pixels, so each pixel will be smaller. That is okay. It is actually what you should do, and is dictated by physics of light. Depending on the wavelength of light and the quality of your lens, namely the numerical aperture, you are collecting more or less data. So you can collect more data just using a different wavelength. You can focus the light to a smaller beam if you use a shorter wavelength. So you can acquire more information when you use shorter wavelength. When you want to acquire the image in the best possible way, remember to set an optimal format while you are on the sequence that uses the shortest wavelength. Once you have done this, you can click Start. Both channels will be acquired and will be displayed on the right hand side. You can decide to switch on or off the channel that you want. The image is already acquired. You can decide to display an overlay of the two channels. You can decide to display only the overlay of the two channels. Once the image has been acquired, it can be displayed in several ways, and annotation can be added for your convenience. You can decide which channel to display, change the display brightness of different channels that will be reflected on the overlay image. You can add scale bars, or clicking on the annotation button, you can add arrows that are very useful to pinpoint specific structure. If you add an arrow on one image, it will be automatically added exactly in the same position on the other image. So it is very useful to check if a structure is present on both channels. So you can zoom in, have a look. You can move the image around. You can add markers. Remember to select the color before trying to add the marker, otherwise it's not going to work. For example, here I'm looking for the yellow color, click OK, and now I can add markers. Again, if I add a marker on one image, markers will be displayed on the overlay image and on the other channel too. That again is very useful to count objects. If any of these markers or arrows needs to be moved or cancelled, you can select them all and then delete them. You can define areas. These areas will be measured in terms of size and mean intensity, a little bit more on image processing and quantification later on. And that is pretty much everything regarding basic annotations. Now that you know how to acquire an X and Y image, I would like to show you how to capture a 3D image. This one is quite common on a confocal microscope and is relatively easy. It is achieved acquiring a sequence of X and Y images and moving the focal plane along the Z-axis, and then the sequence of images are reconstructed on a single 3D one. So first of all, you need to have your image, your 2D one, having the channels settings properly. And then you need to go in live mode, selecting one of the channels that will be used for you as a reference to acquire the 3D image, and setting with the one that will be the starting and the ending position of the 3D acquisition. So basically you need to move the focal plane to the top and to the bottom of your volume. Click Live. Select the channel that you want, green in this case, and click on the Z Stack tab, Begin. You can select the false color. So you can move, you should move the focal plane where you would like to start your acquisition, clicking Begin. Then you move the other way with zoom, with the focus knob, and click End. And that is pretty much it. Here you can see on the display on the left what is happening when you move the focus up and down. Basically the lens is actually moving and you're moving the Z position in a different place. So now that you're ready, you can click Start and you will acquire. Note that the system will set the acquisition in system optimized mode, selecting the optimal interval between an image and in a focal plane and the next one. Using the 10x lens, in this case was 2.41 micron. You can change it if you want, if you don't need full resolution but you want to increase speed. Otherwise, I suggest you to keep it in system optimized to get the best image possible from the microscope. You click Start Acquisition and then you can see on the right hand side the slider moving, showing that the first channel has been is acquiring. You see, going from slide 1 to number 13. First channel. Then once you get there, the second channel will be start acquiring, going from slice 1 to slice 13. In the meantime, the third image represents the overlay of all of them. Once the 3D image has been acquired, you have several ways to revisit the image itself and visualize it. First of all, you can move the slider that will show you the different focal planes. You can change the colors. You can create what is called maximum intensity projection. Clicking Max, basically all the 13, in this case, images that you have just acquired will be just flattened in a single one, getting the brightest pixel of each image. This one is very good to visualize in a very sharp single image the image that you have just acquired, but remember that you are going to lose the information regarding the 3D volume, because basically you have just transformed a 3D image in a 2D image. However, it is very good for visualization. Just click it max again and you will get the 3D image back. You are not going to lose anything. Otherwise, you can go on the 3D navigator, clicking 3D, a new window opens, and then here you can visualize and manipulate in different ways your 3D image. All these visualization modes can be saved as a snapshot or can be saved as a movie. So you have complete freedom and it is up to you to decide what to do. Some of these images are very good for displaying on presentation. Some others are better, best suited for print version. So here you see your 3D image. Just move mouse on the screen and you can see the image moving. You can add frame, axis, scale bar. You can decide to visualize 2 channels or adding the overlay, moving it around. You can zoom in using the mouse wheel, as I'm doing now, going in, going out. Each one of these images, as I said, can be saved as a snap. You can change the color of a channel if you don't like it or if it makes easier for you to see it. Or you can change from a classic 3D visualization to the so-called cut view that allows you to see both the 3D on the top right, but also the three single planes, that is X, Y on the bottom left, X, Z and Y, Z at the same time. This is very good, and again you can zoom in and save it as it is. Just click Save Image and you can save it to a project or a TIFF, JPEG. I'll tell you later on about this. You can add movement to your image once you go back to the classic 3D visualization. You can click Auto Spin. Basically, once you virtually touch your image, it will start moving on the direction that you have pushed on. All this movement can be recorded as a movie, including zooming in and zooming out. This is very good for presentation when you want to display the full image, but at the same time you want the audience to focus on details. You can create a depth coding image where you lose information about the two channels, but the false colors will give you information about depth. You can decide to have the visualization to be focused on a 3D transparent like image, selecting maximum, while volume, before the option that you were using before, it is best suited to display in the best possible way the surface. Once you're happy, you can go back, minimizing the 3D navigator, to the main window to go on acquiring more images. Once you have finished acquired all your images, you should save your file. To do this, you need to move from the Acquisition tab here to the Open Project tab. Once you are there, you will notice a main file called Project, in this example, plus 3 additional files within it. The way Leica file structure works is that it will create a single .lif file where all the images are stored. From your point of view, this lif file looks like a single file, but it is actually like a folder. It is a container. In this case, in the lif file called project, we have 3 files. The first one is a single image that I have acquired. The second one, this one in red, is the 3D file that is a series of single X and Y images, and then a snapshot that I took while I was on the 3D navigator. Each one of these files, including the main one, project, can be renamed. So as you can see here, I have the single file, and this is the project one. So if you right click on it, you can rename it as you want, test in this case, and you can do the same with any one of the other files. It is up to you if you want to do it while you are on the machine, or you can do it afterwards using the free version of LaSex that is called LaSex Core, that you can download for free. Now, very importantly, when you save files, you need to save them into a specific location. So you just click Save As, go on Data E, User Data. Once you are there, you will see a list of folders with the names of the months. So you pick up the right month, you click inside it, and you choose a folder with your name. If you don't have it, of course, you can create a new one. Then, within it, you should save your file. If you do this, the files will be automatically backed up overnight into our server. That will make sure that you have always a safe copy. However, remember that in the bioimaging servers, files are stored maximum for a year. So it is your responsibility to save them into your local machine or your laboratory server storage place to make sure that data will not be deleted permanently. If you don't want to save the file as a LIF, but you want to export it in a different format, such as TIFF or JPEG, whatever the reason it should be, remember JPEG is a format that will lose information, so it's not going to be good for analysis, but only good for presentation, so be aware of this. You can do it again on the Open Project tab. You simply right click on the image or images that you want to export and just select the format. You can also export the images directly to Huygens. That is a software that allows you to deconvolve the images. I will talk later on about deconvolution. Once you have chosen your export format, just click on it and select the folder that you want. More importantly, if you want to have a look of the properties of your image, you can right click on the image and click Properties. This will give you the full details of any single parameters that has been used to acquire the images. All this list of information is called metadata, and this is saved always within the LIF file. This is really useful for you if you want to go back in a few months time or even a year's time and look at what you have done. So you don't have to write down any parameter that you have used, just look at the properties. Even more importantly, these parameters can be reapplied to your following experiment. So all the settings that you have prepared for the experiment that you have tried now as a test don't need to be remade from scratches every time. Actually, if you want to acquire a series of experiments, a series of images, and you want to compare them, you should always keep the same settings. This is very easily done, just right-clicking on the image and select Apply Image Properties. So the properties that you see now scrolling on this document can be reapplied to any image that you want. So, for example, you select the image that you want to take the parameters from, series 2 for example, go on Apply Image Settings. You click it, and then the following image will be acquired with the exactly same settings, that you have used for series 2. So, if today you're acquiring an image and a week later you want to acquire another image with exactly the same settings, you just reopen the LIF file, you look for the image that you want to get the informations and the properties from. You right click on it, you apply the properties, and then you simply start acquiring with exactly the same parameters as you did the week before. Very convenient.
This video shows you how to shut down the Leica SP8 STED microscope and clean an immersion objective. Using the touchscreen, press the Z Control tab and then hold the Move to Load button to bring the objective down. Tilt the condenser arm back to allow easy access to the sample stage and then remove your sample. If you've used an oil immersion lens, clean the objective. Use a single piece of lens tissue folded in half and wipe the excess oil from the objective. Next, repeat the process using a dry portion of the lens tissue or a fresh piece wetted with alcohol from the dropper bottle. Lastly, with a clean dry piece of lens tissue, wipe off the remaining alcohol residue from the objective and clean any spillages from the stage. Now you can shut down the system. Ensure you have saved all your images and shut down LASX software. On the left of the microscope, switch off the HXB fluorescence lamp. Then, on the PC table, turn the laser key off and switch the laser power, scanner power and microscope off with the 3 green buttons. If the STED lasers have been used, switch them off with their key switches and power buttons where required. Now, switch off the compressor at the wall plug adjacent to the room door. The 4 wall plugs behind the system monitor can be left switched on.